Hi, my name is Mia Kramer, and I'm going to be talking about AtomicSets.jl, which is a Julian framework for doing structured optimization. Thanks for coming to the talk, and let's get started. So first I want to touch on a little bit of background information, and specifically on convexity. So convexity just generalizes our intuitive notion of a convex polygon. That's one that doesn't have any caves or dents, to more general sets. And one definition we could use is that a set is convex if for every pair of points you pick in the set, the line between them is also in the set. On the left here, I have a convex set and a non-convex set. Then we say a function is convex if its epigraph is convex. So again, here is a convex function and a non-convex function. Convexity provides a lot of useful properties that allow us to build efficient optimization algorithms, but there are limits to these general purpose algorithms. And structured optimization aims to take advantage of any structure we might expect to find in the solution. The way we do this is by prescribing a set of atoms from which we can build solutions more efficiently. So for example, if we know that our solution should be a sparse vector, we would expect it to be built from a small number of basis vectors, and so those are our atoms. Or if we expect our solution to be a low-rank matrix, then again, we would expect it to be built from a small number of rank 1 outer products. And AtomicSets.jl is a general framework for doing this kind of structured optimization. So let's talk a little bit about atomic decomposition. So if we take our atomic set, which is just the set of atoms of interest, but it can be any subset of a real vector space, we define the atomic decomposition of a vector with respect to that set as the sum of atoms in the set, with the restriction that every atom has to have a non-negative coefficient. So if we consider the one ball, which was our set of interest for finding sparse vectors, we define that as the positive and negative basis vectors in our vector space. And generally what we're interested in is the atoms in our set that participate in the decomposition of a vector, which we call its support. So we have here, I have the 4 atoms in the two-dimensional one ball. I have a vector, and then I've highlighted in green the atoms in the set that participate in that decomposition. Okay, but in order for our set to be general, we need a common set of operations on these atomic sets. First of those I want to talk about is the gauge function, which asks what is the smallest scaling of our set such that the vector of interest stays inside of it, which, as it turns out, is equivalent to asking for the minimum sum of coefficients in the atomic decomposition. So there's a tight connection there between the gauge function and the atomic decomposition. The next two, expose and support, are closely related. So the expose function gives us the atom in the set which is most aligned with our vector, and the support function gives us that particular inner product. So as you can see, the functions are defined very similarly. The gauge doesn't always have a closed form solution, but part of our package is a level set method for computing it for arbitrary sets. Let's try to make this a little bit more visual. So here I've constructed a two-dimensional one ball, and I've plotted the 4 atoms. And then using the set, I've calculated the support function for our test vector in red here, and the gauge. And then I've just outlined the boundary of the scaled set according to that gauge function. So as you can see, as I rotate the vector, the exposed point changes, and as do the support and gauge functions. Another example here is the simplex, which is just the positive basis vectors. And so you can see in this region, it behaves pretty similarly to the one ball, but outside of here, since there is no possible scaling of the set such that this vector remains inside of it, the gauge function goes to infinity, but the support doesn't. But as I go into this region, the maximum value the support function can take is 0, which is just the inner product of the vector and the origin. Okay, and the last step we need to have a general framework is a way to build arbitrary sets. So we have a collection of primitive sets here, and we can combine them and manipulate them in multiple ways. So here, for example, I've constructed a set which is the Minkowski sum of the two-dimensional simplex and a scaled version of the two-dimensional one ball. You can see all of those atoms here, but of course, as I rotate our test vector, not all of those points are going to get exposed, and you can sort of see the outline of the convex hull there. We can also take the Cartesian product of sets, which then lives in a higher dimensional space, or we can apply arbitrary linear maps to our sets. So here you can see I've applied a random linear map to our two-dimensional one ball. All right, let's go through a quick example of one possible use for the set. So what we're going to do is multiplex and demultiplex some sparse signals. And what we're going to do is we're going to generate our k-sparse random signal. So there's just k non-zero components. We're going to generate a invertible random matrix. And what we're going to do then, since we know our original signal is sparse relative to the one ball, we're going to rotate the signal and that set using the random matrix. That's what this does. So here's a pair of random sparse signals I've generated. And then we're going to multiplex them by doing that random rotation and adding them together. Now, to take the opposite direction and do the demultiplexing, we take the Cartesian product of all of our sets here, and we're going to solve for the gauge function. And this is the level set method I mentioned earlier, and so that actually does the atomic decomposition, which gets returned into the solution. And so, of course, we found the signals that are sparse relative to one atomic set and sparse relative to another. We built this solution here, and then by keeping the top k signals of the part of the solution corresponding to the first signal, you can see overplotted here, we have the original signal and its recovery, and then at an offset, we have the error. Okay, so a couple more examples of things that we can do. Since matrices themselves form a vector space, we can work with matrix-valued sets. So one particular example is using the Schatten p=1 ball or the nuclear ball for low-rank matrix problems, or we have a spectroplex. And a couple other examples are linear programming and then regularization problems like lasso and elastic net regression. That's the talk. We should have a few more examples in the repository, and I hope you'll check it out. And thank you for coming to the talk.